Hello everyone. What we have seen so far is the classical BSM model. Classical BSM model, by which we mean that with one stock and with constant parameters, wherein the one stock is the price of that one stock, the price process essentially is given by the geometric Brownian motion, and the growth factor is simply given to be the continuous time compounding factor, which is basically, and we described this model with these two equations, which is under the actual or real world probability measure P, okay, and we considered V capital T to be a derivative, which is simply an Ft measurable random variable. It could be path independent or it is path dependent. Then we derived the risk neutral pricing formula, which is given by this expression here, which is Vt equal to E tilde of e to the power minus r t minus t times Vt given Ft. So, the price at time t, this is the no arbitrage price at time small t of a derivative which is going to mature at capital T. Of course, this is a European derivative what we have. Then its price at time t is simply given by this particular conditional expectation, right. So, you see now where the conditional expectation we are placing, right. So, the price of before time, at any time before maturity of a derivative is given in terms of the conditional expectation, right. So, that is why we said the conditional expectation plays a critical and major role in this risk neutral pricing theory. Of course, if you are using replication in the other way around, of course, which is what called APT approach to the pricing, then of course you will not encounter this risk neutral pricing measure, right. So, this is, so we also have two probability measure P, which is actual or real world probability measure, P tilde, which is basically the risk neutral probability measure. And what are the properties of this risk neutral measure? We have seen it should be equivalent to P, and it should make the discounted asset price processes in the model a martingale. That is what is the properties of this neutral measure. Precisely that is what you have seen it in the discrete time model also. Recall 1 plus r was equal to u times p tilde plus q times t tilde, sorry, plus d times q tilde is what we had it in the discrete time. So, similar things is what is happening here, that it reduces the mean rate of return to r under p tilde. Okay. Now, we have derived this and we have considered at least one case of Vt, which is the European call option, and we have derived the BSM formula. Now, given any Vt, you just have to exactly follow the same process to derive the risk neutral pricing formula for any other derivative, which is in our case simply is an Ft measurable random variable. It could be path independent like an European call and put and forward contract or any such thing, or it could be even path dependent, which is what will happen exactly if you consider the more you go out of this plain vanilla options, right. Plain vanilla options, we mean this simple European call and put cases. If you go out of that, then what you get is what we call generally an exotic options, and for any exotic options to get the price, what you need to use is simply this risk neutral pricing formula. You just evaluate by plugging in this Vt and you get under this model setup the price, which means assuming the geometric Brownian motion evolution of for the underlying risky asset, you will get the thing. Now, the risky assets could be even changed to some other things. Of course, that is what you go as you go along, but we will not get into that. So, what we have seen is this is the risk neutral pricing formula. Okay. We are given, you can, as an exercise, you can try for some other simple Vt functions, which are functions of St, right, like European put and forward contract, which you know already the formula, but you can try to derive them using this residual pricing formula. Okay. Now, coming back to this derivation of this formula relied on a key fact that you could be you could able to find an initial wealth x naught and a portfolio process delta t, right, which tells you number of shares that you should hold at each time t, such that x at capital T is the wealth at capital T is equal to the payoff of the corresponding derivative, right. So, that means that this is, so there is a portfolio process is what the existence of this portfolio process is what you have. Okay. Once, so this means that relied on this formula relied on the fact that there exists an x naught and a portfolio process delta t. You do not need at capital T, but you can, even if you have it, does not matter, because then such that, okay, there is, this is what, such that your x at capital T equal to v at capital T, and hence you are done. So, this the corresponding the wealth at each time is what you call it as the price of the derivative. Now, the question is like, how do we ensure, so because as we see, the discriminatory pricing formula has to be accompanied by the corresponding hedge. If not, then the formula might be questioned, right. So, what is the hedge? Whether there exists a hedge is what is the question that we are trying to answer. Okay. So, in this case where there is one stock driven by one Brownian motion, right. So, let us look at the case first, and later we will generalize this to the multiple or multidimensional BSM model. Now, this relies on what is called based on a result. So, the question that we have raised can be answered with the help of a result which is called Martingale representation theorem. Martingale representation theorem, we might simply call MRT, okay, and this is in one dimension is what we are looking at it, means with one Brownian motion case that we are looking at it. Okay. So, what is the result? Of course, you are not going to prove this result because the proof is involved. So, we will just take the result as given and we will try to use this in our case to justify whether there about the existence of this delta t. Okay. So, what we have here, let you have a Brownian motion be a Brownian motion on omega f p, and let f t be the filtration generated by this Brownian motion. Okay. Let you have a process MT be a martingale with respect to this filtration. Okay. Right. Then there exists an adapted process which is in more generality, some gamma t such that you have mt is given by m naught plus 0 to t of gamma u dwu. So, this is the result. Okay. So, now there are two crucial points that you need to look at, that the filtration is generated by this Brownian motion. So, here what we have, your f t is actually f t w. In our earlier notation that we have introduced, that this f t is actually f t w, which is the filtration generated by the Brownian motion only. Okay. Right. So, that is what you need to understand, the critical point that we have here. Whereas Girsanov theorem, it could be any general filtration, which means the filtration in Girsanov theorem could be larger than the one generated by the Brownian motion. There could be other random variables which could also be part of the generating class for that say filtration. But in this particular case, it has to be precisely, it has to be the same as, which means that what, since we view f the filtration as information contents. So, what this is saying is that the information that you have by observing Brownian motion starting from 0 up to time t is exactly the same as the one which is there in the filtration, right. So, that is what is okay. Now, so what this says is that now in this setup, if you have a martingale with respect to this filtration, then this filtration, this martingale can be represented, that is how the name comes, as a constant plus an Ito integral with respect to some adapted process gamma. Okay. So, that is what. So, this is an Ito integral, this martingale can be represented as an Ito integral. This is in this simple setup, this is what you have as the martingale representation theorem. Okay. The relevance of this result to our problem, which is hedging, is that since f t has only one w which generates this f t, so there is only one source of randomness, right. The only source of uncertainty in the model is the underlying Brownian motion, and hence there is only one set of source of uncertainty that is to be removed by hedging, right. So, that is what it means, and since MT in this particular case if you look at, so this assumption implies that because this is given in terms of Ito integral, and since Ito integrals are continuous, so this martingale cannot have jumps, and if you need to have jumps, of course you need to introduce more random sources than W that is have, right. So, that is what would be. Okay. Now, the fact so, what is the restrictive assumption here is this filtration. Now, this and the other Girsanov combinedly can be written as a corollary. If you write a corollary which combining these two, right, even in the case, so what you have, so you have W t where t in 0 to t on omega f p, okay, and you also have this f t w, okay, which is a filtration. So, this w t is there and then f t w is a filtration. Okay. Then if you pick, then for theta we define my z t to be e to the power minus theta w t minus half not sigma theta square t and w tilde t as Wt plus theta times t, right. Then set z equal to t, then expectation of z equal to 1 and under p tilde defined by this our usual definition. Okay. The process W tilde t is a P tilde Brownian motion, right. This is what is the first part. This is exactly the Girsanov, except that the filtration now we have shrunk a bit to make it equal to FTW. Now, in this particular case, right, now let m tilde t be a P tilde martingale, then there is an adapted process, say gamma tilde t, such that all these time periods are all t belongs to 0 to capital T, that you remember. M tilde t is equal to m tilde 0 plus 0 to t gamma tilde u dw tilde u, okay, for 0 less than or equal to t. At the outset it might look like we have just combined Girsanov and MRT by reducing the filtration to the one generated by W. But if you look at little bit more closely, this is little bit more than that, right. Because the first part is fine, there is no problem, but the second part when you pick it up, you know, you are talking in not in terms of P, but in terms of P tilde, and the W is a Brownian motion under P and FTW is the filtration generated by that W. But even then, you know, this result holds even under W tilde, okay. So, that is what is the little bit detail that you can look at it. But of course, that is if you wanted to look at little bit more closely what exactly is happening, that is what is happening in this case, okay. So, this is the corollary part that we have, which is true. So, which means this martingale representation theorem, right, when we come to this P tilde, we are still taking not FTW tilde, but FTW as the filtration, and even another filtration, this adapted process means this is adapted to that filtration, and still this is true, that is what it is. Of course, the proof you can see if and how and when, and it is true, okay. Now, let us come back to the hedging problem. So, this is the result. Now, we have combined and we have written this corollary. Martingale representation theorem is what is going to help us you know, to establish that there is a portfolio process delta t, and hence the Risk-Neutral formula is valid and it holds true, okay. So, let us come back to this, and then now we come back to hedging with one stock in BSM, of course, the classical version, right. Now, assume the filtration to be FTW only, okay. In the earlier we have said did not put any restriction, but now if you want to show the existence of delta t, then you need to put this restriction. So, this is what it is now, okay. Now, we take Vt and Ft measurable random variable. So, which is what is the derivative in our case, okay, and Vt from the risk neutral pricing formula So, we have e to the power minus R t V t is e to the power minus R t V t given f t. This is what we have, right. So, this quantity is a p tilde martingale, right. So, e to the power minus R t V t is p tilde martingale, right, because that is what exactly this statement also would mean, or you can even show that you can take this left side condition on f s for s less than t under p tilde and show that this is martingale, which is one and the same. So, this is we can easily see that this is. Now, therefore, this is a p tilde martingale, and hence by applying the result MRT and its corollary, this has a representation. So, this implies this has a representation as e to the power minus R t V t is equal to e to the power minus R 0 times V 0, which is simply V 0 plus 0 to t of some gamma u d w tilde u for 0 less than or equal to t, right, for adapter. Okay. It may be turned out to be simpler in this simpler case, but we are writing in general as it is. Okay. Right. So, this is what we have. Suppose if I call this as let us give the name a little later. Okay. So, this is what is the first fact that you. Now, on the other hand, we have also seen for any portfolio process what is the differential of the discounted value process. Okay. So, what you recall? Recall that your d of e to the power minus R t x t is delta t sigma e to the power minus R t s t t w tilde t, right. So, you recall this means what? E to the power minus R t x t equals x naught plus 0 to t delta u, okay. Sigma I can write it outside, or let me keep it inside itself, sigma e to the power minus r u s u d w tilde u for 0. So, this expression we have obtained earlier, the discounted wealth process of any portfolio for any delta. Okay. Now, what we need to have? We need to have, in order to have x t equal to V t for all t, we should choose what we have to do, x naught equal to V naught and choose delta t to satisfy what we have, delta t sigma e to the power minus R t s t equals gamma tilde t for 0 less than or equal to t. Now, how did we do? So, you look at the representation of e to the power minus R t times V t, which is this V naught plus this Ito integral with integrand as gamma tilde of u. Look at e to the power minus R t x t, its representation x naught plus this Ito integral with respect to this integrand coefficient that is given here, right. Now, if we need to have, which means that we want to ensure that there is a delta t which ensures, which gives or which gives us an initial wealth as well as a delta t such that what we want is xt equal to Vt. What we want is xt equal to Et, which means we want this can be achieved through making it x naught equal to V naught, and look at the integrand here and the integrand here. If these two are equal, then this is what we have done, right. Now that is, so what is this means? This means my delta t is essentially gamma tilde t divided by sigma e to the power minus RT times ST for this. Okay. If I pick my delta t to be equal to this, right, with this choice of delta t, right, because I know there exists a gamma tilde t and sigma is given by sigma R S, all these quantities are given in the model. So, if I take this as the position, then we will have xt equal to Vt at all time t, and hence x at capital T would be also equal to V at capital T, which means we can completely hedge. Okay. So, this is the thing. So, the two key assumptions that makes this happen is that sigma is non-zero. Okay. Note, sigma is non-zero is one of the assumption. If sigma is 0, of course, the stock itself like sigma is 0 means that is gone. So, then the only risk free assets that you have, you really do not have the risk free assets. So, but typically we said it sigma is strictly greater than 0 because it gives the volatility term, and that means that this quantity is well defined, delta t is well defined, right. The other assumption is FTW is this is the filtration. So, this is what is the two key assumptions for existence of this hedge, okay. Because this is only one randomness Ft generated by the underlying Brownian motion, which means that there is no randomness in the derivative security apart from the Brownian motion randomness which is there, which is can be hedged by trading in the underlying stock itself. Okay. So, under these two assumptions, every, which means that every Ft measurable random variable, right, which is basically every derivative security can be hedged in this model. So, and such a model is said to be what we call complete. So, this is the meaning of derivative security, here we mean European type of course. So, this is every derivative security can be hedged, which means that there exists an initial wealth and there is a portfolio process which will hedge the position, the short position in the derivative security, and if the model allows such a thing to happen, then that model is said to be a complete model, and obviously we would want that we have a model which is complete, so that we can hedge and we can arrive at the price, because the price is justified when only when you show that you can hedge the short position in the underlying derivative security, right. So, this basically the justification, but what is lacking here is that you look at this delta t gives only an expression which involves gamma tilde of t, but the gamma tilde of t we do not have an expression for gamma tilde of t. What MRT says is that there exists a gamma tilde t. That means since we cannot explicitly compute from there the what is gamma tilde t. So, the existence of such a portfolio which will hedge the short position in the underlying derivative can be proved using martingale repression theorem, but you really cannot directly get what is that position, right. For positions, of course, we have to rely on other methods. Of course, one of them is we have seen earlier, right. For at least European call option, you have seen the delta hedging strategy is what is given by the delta hedging rule. Okay. So, only MRT guarantees the existence, but for computation, okay, method of finding either gamma of tilde of t or delta t, you have to rely on some other techniques that we have it here. Okay. Now, so this is what is our discussion on the single Brownian motion case or a classical BSM model with constant parameters and one Brownian motion which is driving the randomness, and there is one stock, that is what we had it. So, in this classical we have obtained the risk neutral pricing formula and we have justified it by establishing a hedge, that is what is the theory. Now, we will want to move to the multi-dimensional case, but for which first we need the Girsanov multi-dimensional Girsanov and MRT before we specify or describe what is the multi-dimensional BSM model that we have. We are going to look at it. Okay. Now, in this multi-dimensional, so what we are having now is let us for the time being write this as within bracket, which essentially means 1t, w2t and so on, wdt, which is a d-dimensional Brownian motion, and we know what exactly we mean by a d-dimensional Brownian motion. Each one of them is a Brownian motion, and in addition to that they are independent, right. So, that is what is the case that we have. Okay. So, d-dimensional Brownian motion typically we mean each one of them is a Brownian motion and they are independent of each other, that is what we have now here is a. So, we as usual will have this filtration and other stuff. Now, what is in this particular case Girsanov, how will look like? In this case Girsanov will be that we are fixing. Okay. So, we are also fixing a t which is greater than 0. So, that is we are considering the interval 0 to t as our time period. Okay. Now, what we have is that in this multi-dimensional Girsanov, so what we have, we can write this as theta of t, which is essentially theta 1 t, theta 2 t and so on, theta d t is the d-dimensional vector or the d-dimensional quantity. Okay. So, now actually we do not have the so time dependency. So, we could write theta 1, theta 2 and theta d, okay, because we are in the realm of classical BSM setup only we need. So, we could take constant. So, this is given these constants. Okay. Now, define. So, remember in one dimensional we just picked one theta, now we are picking a d values of theta, d thetas, I mean a vector theta. Okay. Now, define Zt to be e to the power minus the dot product of theta and w, which you can write it as j is equal to 1 to d of theta j w j t minus half, again the norm of this theta, the L2 norm of this theta, which is j is equal to 1 to d of theta j square times t. Remember, in one dimensional we just wrote e to the power minus theta times w t minus half theta square t. So, this is just that the multi-dimensional version that we are writing it, and define this, and w tilde of t which is as W t plus this theta of t. Remember, there are W tilde and W, they are all d dimensional. So, actually the theta, these are all d dimensional. So, actually there are d equations here, essentially what we are looking at it. Okay. Now, you set Z equal to Zt, then you have the usual one, and under P tilde given by P tilde of A Z of W d P of W for A in F. Okay. So, what is F? F is your capital F t. Okay. So, F is F at capital T. You can as well take the F t to be the one generated by the Brownian motion to make it life easier or to understand a bit easier. Under this given by this process W tilde of t is right, now t is a d dimensional Brownian motion. You see that we can also always write this underscore to denote the vector. Okay, so maybe we can do that. This is a vector, this is a vector, this is a vector, this is a vector, so that there is no confusion that is a unidimensional or multidimensional. Okay. So, this is a vector, is a d dimensional Brownian motion is what then you would see. So, this is what is the multidimensional Brownian motion. Okay. So, here it is simple in the case of theta, but if if you want to generalize to a more generic one, of course, there are a little bit involved thing, but here it is straightforward that what you are seeing in the similar way as the other case that you have it here. Okay. So, this last equation is this is actually the W tilde equal to W plus theta times t is actually a shorthand notation for the D equations. Okay. So, this is what you have it as a multidimensional, and MRT in this particular case is that, of course, now in this case we are taking Ft divided by, generated by this vector process, okay, Wt, right, d dimensional filtration generated by the d dimensional Brownian motion W bar, W, right. Now, let in this particular scenario, let Mt be a P martingale right. Then there exists a gamma of u, which is actually gamma of t, let us take 1 t, gamma 2 t and so on, gamma dt, a d dimensional adapted process, adapted such that your Mt is equal to M0 plus this, again you can write it as a dot product, or you can write it as 1 to t of 1 to d of 0 to t gamma ju d w ju, right. So, this is what will be the case, that you are writing it as. So, what is the representation? Any P martingale can be represented as a constant plus d number of Ito integrals. Okay. If in addition we are trying to write the corollary like earlier, if in addition if we assume the, so this is actually the corollary part, MRT is done. So, this is actually corollary condition. We assume the notations and assumptions, okay, as earlier, right, and if your m tilde t is a p tilde martingale, then there exists adopted process which is 1t to t and so on dt, right, such that you will have m tilde t to be equal to m tilde 0 plus summation j is equal to 1 to d of 0 to t gamma tilde j u d w tilde j u, right. So, this is what we might use when we use the, so this is the multidimensional version and this is the Girsanov multidimensional version what you may have to do, that is what is the case, right. So, which means that for getting this p tilde which is equivalent to p in a multidimensional case, what you need is you need to pick some d constants theta 1, theta 2, theta d, define this z t and set z equal to z capital T, then you can see that expectation of z equal to 1 and probability of z greater than 0 is 1 and hence this z is actually the Rn derivative and the zt is Rn derivative process, and under that z you can define a p tilde which is as per this and this will be an equivalent probability measure to that, and this under this w tilde as given here will be a d dimensional Brownian motion, which means each one of them in that component is a Brownian motion and they are still independent. Similarly, MRT a multidimensional version is what then you have. So, the representation is that you have a constant plus sum of constant plus d Ito integrals is what you are going to have when you look at the multidimensional case that you have. Now, let us now move to what we have, this multidimensional market model. So, which is what we are going to see now. Let us describe what is the multi-dimensional. You can also call this as a classical because this is constant parameter 1, but still we will not call in that way. So, multi-dimensional BSM model, okay, is what we will refer to general because. So, what we have here, what is the generality that we have over one dimensional BSM model? Now, we have more number of stocks and more number of randomness that we are bringing inside the model. Okay. So, what we have now is that there are, we are assuming there are n stocks and d Brownian motions, which is what is the randomness count in our case. Okay. So, what we have, the dynamics, the stock price dynamics, how are they given? This is dSIT is equal to alpha I SIT dt plus SIT summation j is equal to 1 to d sigma ij dWJT for I is equal to 1 to m. Okay. So, let us call this as the the description or the description of the evolution of the stock price processes. Okay. So, here we see this sigma ij's we typically assume to be non-zero quantities such that this matrix of sigma ij's are invertible. Okay. So, that is essentially you can justify that by assuming that you are trying to have inside the model the quantities which are not really can be expressed in terms of the other ones. If one stock price process can be expressed as a linear combination of the other, obviously then you will not keep that because it may not be useful, right. So, you will have a slightly independent or a little bit of that nature. So, naturally then you will get this required quantities, but you will not worry too much about that. So, these stocks are typically correlated, okay. So, they are not right. So, it is not linear perfectly correlated, but it will have some correlation coefficient, that is the situation that we have it in mind, okay. So, these stocks are the stocks are typically correlated, okay. Now, how do we see? Okay. What we will do is that we set or we define sigma I square to be j is equal to 1 to d c I j square, and we will assume this is not equal to 0, we assume, okay, because we are going to divide and so on, and define a quantity which we call BIT to be summation j is equal to 1 to d sigma ij by sigma I times Wj for I is equal to 1 to m. Okay. So, now you had the stock price dynamics which is given by 1. Now, you see that the stocks are typically correlated, which we want to see. So, we will define a sigma I square which is nothing but the sum of sigma ij square for j sum over j, and we assume that to be not 0, and define BIT. There are m such processes, BIT m such processes using this quantity and sigma I which we just defined, okay, right. We can define from this using dw's, we are defining m b's. Now, what are these b's? Let us look at little bit more closely. Observe that each of this BIT is continuous, easily you can see, because they are sum of W's which are continuous, and also they are martingale, okay, which also you can see. Further, you can see that dBIT, what you would get, because you will have only the corresponding terms will come, because Wj's are independent. So, you will use the standard formulas to arrive at this sigma ij square by sigma I square dt. So, only Wj will remain. So, this is what you will get, and this is nothing but dt, which means the quadratic variation of Bi with itself, or the quadratic variation of the Bi process is 1 per unit of time, right, which is a continuous martingale, starts at 0, okay, 0 at time 0, and quadratic variation is this, and all these things put together. Now, what this is imply? my Levy's criteria or Levy's theorem implies that each of these is a Brownian motion, right. So, this is what we are using. So, the Levy's criteria tells that each of these this. So, we can rewrite one as the original equation as dSit as alpha I Sit dt plus sigma I Sit dBit. Of course, this I can call this as 1 dash, okay, where this is now you can easily see volatility of SIT, this process, volatility of this process. Okay. So, we have written there. So, this is an expression which we have written in terms of Wj's which are independent Brownian motions. Okay. So, you have these coefficients and this is a long expression. Now, by defining BIT, which is also Brownian motion, BIT is, by the way, is also Brownian motion. If you want to write, then basically you can, for ith stock, what is the volatility if you want, because from the previous one, right, you can compute this sigma I, which as we have defined there, and this is the volatility of the ith stock, as you can see from here. Okay. Now, for I not equal to k, for I not equal to k, so this BIT and BKT are not typically independent. If they are independent, of course, this is a much simpler situation that we are thinking about, but generally they may not be typically independent. Okay. So, how do we see? Note, or what is their, how do you define or what do you get as their dependency? Look at first BIT and BKT, which is from here is essentially you can see that from the definition of BI and this. So, this is J is equal to 1 to D sigma Ij and sigma Kj by sigma K dt, which let us call this as rho I K dt, where my rho I K is this quantity. Okay. My rho I K is essentially this quantity. Now, take take this quantity BIT into BKT, and from Ito's product rule, what you get is D of BIT BKT is equal to BIT d BKT plus BKT d BIT plus dBIT dBKT. Now, you have seen why we computed that quantity to be. Now, this if you integrate, right, if you integrate this, what you would get? BIT BKT is equals integral 0 to t of BIU dBKU plus integral 0 to t of BKU dBIU plus this quantity we have already computed to be equal to rho ik dt, right. Now, if you integrate that, what you would get? You would get rho ik times t. Okay. Now, we can write the covariance term, right. So, this So, covariance of BIT, BKT, because each of them is expectation is 0. So, this is nothing but expectation of BIT, BKT. Okay. So, this BIT, BKT is given in the previous line. Now, if I take expectation of that, and since the first two are Ito integrals, which if you take expectations they become 0. So, you end up with simply rho I k times t, which you can write it as rho I k times square root of t multiplied by square root of t. So, then what does this means? So, this is means that this is the correlation coefficient between the processes BIT and BKT. So, this is the correlation coefficient. So, you can see that the covariance is given in terms of this rho I k times, because each BITs are Brownian motion. So, in an interval of length 0 to t they have the variance t. So, standard deviation is square root of t. So, this is that is what we have written here. So, this means that this coefficient what we have written is actually the correlation coefficient of the processes BI and BK. So, you can represent the multidimensional market. Okay. So, just quick recap. The first step is essentially you can DSIT you can represent in this form where WJSTs are independent Brownian motions, or you can write as it is in 1 dash with sigma I as its volatility parameter, and through this SDE essentially the dynamics is given by through this SDE. Then these BIs are correlated with the correlation coefficient rho I k as given in this expression, which is again you can write in terms of sigma I and sigma ij, sigma kj's and so on. So, this is what it is have. So, this is what is the description of your risky assets case. Now, we also need to give as usual the risk free asset, as usual the risk free asset which could be either a bond or which is same as the single dimensional model. There is no doubt B not equal to 1 or Pt equal to e to the power RT. Equivalently, you can also write using the discount factor, right. So, again d not equal to 1 or dt equal to e to the power minus RT. So, this defines this. Okay. Now, we look at the discounted stock price process. Okay. What is the expression? SIT to be equal to minus R e to the power minus RT SIT dt plus e to the power minus RT DSIT, right. This is what you get by Ito's formula by making this function. If you write, then that is what this is what you will get, which you have seen already, alpha I minus R e to the power minus RT SIT dt plus e to the power minus RT SIT summation j is equal to 1 to d sigma ij dwjt, or you can write it in terms of the alpha I minus R e to the power minus RT SIT dt plus e to the power minus RT SIT sigma I dBIT for I is equal to 1 to m. let us call this as equation 2. So, we had equation 1, now this is equation 2 that we have, which is the discounted stock price process either in terms of W or in terms of B that we have written down here. Okay. Now, once we have this description, now we can next what we will look at is basically the first part of the two-part story, which is basically the existence of risk neutral measure, if what does that imply, and then the second part of that is that whether how many such risk neutral measures are existing and what does that imply is what then we will look at in generality. Of course, we will take that discussion in the next lecture. Okay. So, you remember these things, of course, we will recall and then we will proceed in the next lecture that we have. Thank you.